Good afternoon, everyone. Thanks for joining today for our webinar on using relevant data. We're just going to hold on for a few more minutes for anyone else to arrive, and yeah, we'll start talking through it in a few minutes. Okay, so thank you all for being here today. We'll make a start on the webinar today titled Avoiding Catastrophic Failure of Your Process Using Relevant Data. My name's Dr. Ollie Armstrong, and I'm the Chemical Process Evaluation Laboratory Manager here at Sigma-HSE. I did present a shorter version form of this talk at Chem UK this year, which is a chemical industry conference and show in the UK, but we've sort of fleshed it out and made it longer for this talk today. So normally the kind of webinars that I do cover the testing in my laboratory with chemical reaction hazards, reaction calorimetry, thermal stability kind of tests, but we're also going to include in today some detail and information of tests from the Industrial Explosion Hazards Lab to give a sort of wider aspect on using process safety data to ensure the integrity of your processes that you may have. So once again, thank you for joining, and we'll jump in now. So to give a bit of an overview, we'll first start looking at the background of what we mean by what is a process failure, specifically for process safety. We're not really talking about quality issues and those kind of internal considerations you may have around your process, but specifically process safety. Secondly, why analysis of your normal process and normal operation, but also misoperation is required to ensure the safety of your process. Thirdly, when testing might be needed and when it may fit into your process development timelines. And then finally, which kind of tools are available for both testing to gain the kind of relevant data that you need to use, and then base your assessments on your risk assessments. So hopefully what we aim for you to get out of this webinar today is the reasons behind process safety, potential consequences if it's not done properly, and therefore the importance of it. The potential testing routes that need to be decided upon to be relevant to your process and application, the kind of different assessment options there can be, and how this testing can be relevant to your processes. So here at Sigma-HSE, we've got a bit of a summary of the kind of laboratory testing we can perform to provide you with this data you can use. So obviously talking for myself, we have the chemical reaction hazards testing, we have thermal stability testing, and then in the Industrial Explosion Hazards Lab, we have powder or dust, fire and explosion parameters testing, also gas and vapors flammability, and electrostatic properties. So I've got a video here on the right-hand side, which is of a gas and vapor test called LEL-UEL, which explores the limits of flammability, whether it's a lean or rich mixture. It just gives a nice slow flame, which we can see there. So that's indicative of a lower explosible limit with the blue flame as a lean mixture. And then the image that was up before was the orange flame, which is a upper explosible limit, a rich mixture will show an orange flame. So here at Sigma-HSE as well, we also have our consultancy arm, but also your internal teams can use a variety of different risk assessments and process safety assessments to ensure that your processes are designed and operated appropriately. And again, just as the tests need to be chosen for their applicability, so do the different assessments to ensure that they come to the right kind of conclusions and recommendations. So what is process failure and what do we mean by that? So specifically for reactive systems and chemical reaction processes, they can have an inherent risk of exothermic reactions and or decompositions. So even if the desired reaction isn't exothermic, or it may be endothermic with low risk, there's a potential for decompositions with the materials used and the reagents and the products that can still pose a risk to the system. So decompositions are often exothermic and can and often has also produced gas products. So the combination there of increasing temperature from exothermic reactions, but also the generation of gas or vapors and increasing pressure within a vessel is kind of a two-pronged risk to a contained system. And unfortunately, runaway reactions have caused a number of industrial incidents. Each kind of incident or process without incident has its own niches that need to be assessed and considered. And then for non-reactive systems, such as the dusts and powders, gases and vapors, they still need to be assessed properly and ensured that sufficient controls are in place to handle these materials and process these materials if they've got any chance of forming a flammable atmosphere. So just to recap on some of the incidents that have happened over the years, these are two reactive system examples, which have both been caused by some kind of failure in the process, whether it's in the case of Bhopal, where there was maintenance work and certain valves weren't operated correctly, and incompatible materials mixed. And there was information that these materials should be not mixed, yet it still happened because the controls weren't appropriate or in place correctly. And then in the second example, this is more about it was a reactive system, it was a thermal runaway incident, but it was involving just storage tanks of waste, and it was only the temperature control of the tank which caused the issue. And of course, these incidents can result in loss of plant, cost to the company, in the worst cases, harm or death to operators and civilians nearby. And again, two examples of non-reactive systems which fall under the industrial explosion hazards kind of criteria, sort of what we'd consider inert material, wood fibers, flowers, sugar, other organics. These kind of powders and dusts can form strongly explosive atmospheres when dispersed as a dust cloud. And in these cases, it's normally an initial explosion or event can disperse much more dust into the atmosphere, which can trigger a secondary explosion, which can be much more vicious and less controlled. So taking those kind of examples into account, and the second section of why we think analysis of both your normal process and misoperation needs to be assessed and is required to ensure your process is operated safely. For the industrial explosions section, understanding how a material or mixture is to behave in a normal process. So what is the material you're looking to process? What kind of operations are you proposing to put that material through? Depending on those specific processes will depend on whether you need information around ignition sensitivity, explosion severity, explosibility limits can be used as well to implement controls, any thermal stability issues depending on your unit operations, and also the electrostatic properties of the materials and potentially the plant that you have around it. And then secondly, for reactive systems, understanding on how a material or mixture may behave in a worst case scenario. So how we tie in the information around your normal desired process into what may happen if it is out of control, thermal stability considerations, and any potential for runaway reactions to occur, and what controls can be put in place to mitigate that. And these, of course, are all required due to various regulations and code of practice that companies need to adhere to. And depending on the specifics of your process will dictate which sort of regulations you fall under. So the DESIR regulations are quite wide-reaching in terms of looking requiring any kind of potential explosive or flammable atmosphere to be assessed, or ATEX in Europe. And then the guidance notes from the HSE to do with reactive systems and the kind of design and assessment of reactive systems and plant to operate these within. We also have the UN Transport of Dangerous Goods, and these are a set of criteria and proposed tests for handling materials specifically for transport. And then, of course, in the US and Asia, the other localities, there's other regulations that come into play. And this is not an exhaustive list. There are many others depending on the type of materials you're working with, the size of your plant or your site, and the associated risks with those. So specifically for reactive systems, and trying to demonstrate why we look at normal operation alongside misoperation. So we have a reactive system plot here, where on the x-axis we have time, the y-axis we have temperature, and starting in the region labeled number 1, we have a heating of a reactive batch system, where we increase the batch to our temperature set point to initiate the reaction to generate our desired products. We can then see the scenario where the dotted line would be if the batch completed its reaction while the cooling jacket was maintaining its performance and removing any exothermic behavior from the system. In the light gray zone, we have the scenario where we have a cooling failure. The reaction that is proceeding is exothermic, so the batch of material heats up to its MTSR, which is the maximum temperature of the synthetic reaction. So that is the system self-heating, and there's no removal of that heat from the system by any cooling mechanism. This then triggers a secondary reaction, a decomposition in the dark gray zone in the top right, which again we have a decomposition which is again exothermic, further increasing the temperature of the system, and this is a triggered runaway reaction scenario. So based on the testing and the data that we can glean from it, we can assign each reaction step or scenario into various criticality classes, and depending on which criticality class it results in, certain recommendations can be made about changes that may need to be made to the process to basically lower the risk. If you've got a criticality class of 1, maybe 2, these are the lowest risk, whereas at the high end, criticality class 5, we have a scenario where from the temperature set point at the bottom, if we lose cooling in the system, the reaction self-heats up to this MTSR point, which is past the decomposition onset point within the system. So this is the worst case runaway reaction scenario. And again, with just a simple chemistry example of a simple reaction going from reactants on the left, products on the right. We've got hydrogen peroxide, where energy is put in to put it into a transition state. So this is an endothermic process to reach the transition state. Following this, it falls down to the products of water and oxygen gas, which is a exothermic reaction, resulting in an overall reaction which is exothermic and self-heating if there's no heat removal. But also to note is we're moving from hydrogen peroxide, which is solely a liquid, and we're forming products which are a liquid and a gas. So if we have a fixed amount of hydrogen peroxide, say 2 moles, that will occupy at standard temperature a volume of 47 milliliters. Whereas on the product side, if we've got 2 moles of water occupying 54 milliliters, so roughly equivalent, but this 1 mole of oxygen gas which is produced wants to occupy this 22 litre volume, which is orders of magnitude larger than the starting reactants. So we can see that if we have this gas in a contained vessel, that will generate quite a lot of pressure just moving through this simple reaction. So as part of the assessment into any new processes or re-evaluation of a process, if any changes are to be made, either in materials or operations along that process, the potential causes of these hazards needs to be assessed fully. And there is a lot of different potential causes that can lead to these kind of runaway reaction scenarios in a reactive system. So starting with improper assessment of scale up, moving from small scale R&D of designing a new process through to large scale and not fully quantifying the cooling requirements to service that larger reactor system, but also sort of vent sizing and relief design. If it's just done around normal operation, the process that you want to perform, but not the reasonable worst case that could occur, can be a recipe for a system failing. Also, systems failure, any type of equipment that is servicing a reactor, we don't really want the scenario where any one of these failures or any one of these equipment causing a catastrophic total failure, such as if agitation stops, cooling jacket fails, dosing pump, dosing at the wrong speed, or so on. And then adding to that also process failure, so human errors, incorrect sort of reactive processes. So what is someone to do if a process deviates or outside of its sort of planned state? So all of these need to be fed in and considered during assessment of a new process. And that really boils down to identification of the worst case. And any potential deviations that could occur can only really be identified with detailed knowledge of the material to be processed, but also the plant and whether it is existing or to be designed. And again, there are lots of different available assessments that can be used, and they can even be complementary to each other. So again, as we demonstrated in that hydrogen peroxide decomposition example, pressure really is a key hazard. If you're doing any kind of processing within a contained environment where there's the potential for pressure to accumulate. So rarely will exothermic energy, i.e. an increase in temperature, potentially be a hazard on its own. the effect of pressure increases on a system can be much more crucial. So overpressure within a system can come from three potential sources in a reactive system. It may be slightly different in a non-reactive system or a flammable combustion type scenario. But first, starting from gas generation from the normal process. So that is maybe your normal desired reaction actually generates byproducts of gas, and how we need to handle those, whether they need to be scrubbed out of the system or retained. But either way, that potential for pressure generation needs to be evaluated. Secondly, vapor pressure effect. So any increase in temperature within your system can increase vapor pressure, either from the solvents or any products as well. And then thirdly, like we said, we have that scenario where we lose cooling and heat from the normal process causes secondary reactions or decompositions, which can again, in turn, normally in the case of decompositions, generating gaseous products and increased vapor pressure alongside that. So that's a double threat, really. So just to briefly touch on relief sizing and vent sizing for reactive systems, really it comes back again to having the full knowledge and understanding of the materials and the chemistry within the process. The physical parameters are key to vent sizing. The mass, the design of the batch that is going to be used, what are the products, what are the reactants, what are the products even of any decomposition reactions can have a big impact on vent sizing area. The nature of the mass, again, reactive, non-reactive, any inhibitors present, surfactant potential, making the system more foamy when venting, and of course hazardous properties. So any material that is needing to be relieved from a system, how are you going to handle that effluent safely? Phases, state of matter. So is the material solid, liquid, homogeneous, heterogeneous? This all has a bearing on the design of a system, and will also dictate, on the dynamics and the flow of the effluent. How is it going to react when it's removed from the system? And that will have an implication on the vent sizing area needed. So to come back to the testing and how it might fit into a new process design, this kind of flow chart is more geared towards reactive system design, starting from early stage R&D, where we know what we want to produce, and we're looking at how we're going to go about producing that and what kind of reagents and processes we can use. At this point, it's good to do literature searches, use some calculations to try and get a feeling for any potential hazards of operating this system. And then moving from this point into testing when there's a bit more certainty around exactly what materials are going to be used or proposed to be used. The thermal screening can help. If there's a few candidate reagents to use, if you go through thermal screening at this point, we might find that some of those candidates have quite undesirable thermal stability characteristics, such as low onset temperatures for decomposition. So other candidates can be favored at this point. And then when we've fed that back into our sort of synthetic route design, we can start looking at reaction calorimetry. How exactly are we going to introduce these reagents to each other, dosing rates, mixing requirements, and the inherent adiabatic temperature rise of these desired reactions. That will also help on the design of the plant or choosing certain reactors that this new synthetic route can fit into, alongside which sort of early stage hazard assessments can be made when looking to going towards pilot plant scale and proof of concept. So when we're looking at operating a pilot plant, again, we start looking at major hazard assessments before we move up to production scale, because again, the scale of risk is that much higher at bulk scale. Adiabatic calorimetry can complement this also, where we may want to retest any materials that were highlighted during the thermal screening stage of any particular concern, or also if the reaction calorimetry has shown quite a large potential for the system to self-heat if you lose cooling, that may also point to the need to do more adiabatic calorimetry, just giving greater certainty around onset temperatures for decompositions, and can also be used to start looking at vent and relief sizing. So the complement of all of these testing at different stage and the different assessments should finally feed into your basis of safety specification to be able to operate your process at production scale. So this is a typical kind of assessment strategy that can really be a good guide to tick all the boxes to ensure that we're not forgetting anything when we're designing a new reactive system process. And it highlights various points where if there's any region of interest or particularly high risk, it kind of prompts to make modifications to the process to ensure it can be operated more safely. And this can be iterative. So any kind of small changes or abnormalities that can occur in the process, we should prompt us to go back again to early on in the process and reassess that we know that everything has been assessed fully. So finally, after that background, we can look at which kind of tools are available to ensure you have your relevant data for your assessments. So key to this really is that testing options and assessments should be chosen for their applicability and their relevance to your process. Of course, we can test a material for every kind of parameter available, but only some of that is actually going to be of any use for your assessments. So just ensuring that it's aligned with your process and what you need is of use. So to decide on this, what are the parameters of the desired process? Is it reactive, non-reactive? We'll have some guiding. Any particular or applicable regulations for the process as well will dictate the level of testing assessment needed. And also, if there is any existing data, whether it be small scale screening, literature values, that will help decide and inform on which tests will be most appropriate to further the assessment. So to look first at some chemical reaction hazard testing types that we can perform. So our screening and thermal stability screening tests, as we showed before in that kind of flow chart, these are useful to perform at early stage of a process development, and will give good indication if there's any particular risks around certain materials or mixtures. So these are useful for that early stage screening because they tend to be typified by lower sample requirements, the speed of the testing and the sort of ease of the analysis. Some of them are easier than others, but again, that feeds into the turnaround and the simplicity of the tests. Again, just kind of highlighting any potential issues with materials and mixtures or products. They are indicative of more accurate testing, which can come later on in the process, adiabatic methods and so on. So as they are screening tests, they are lower accuracy. The tests tend to have a higher phi factor, which makes them less representative of a bulk scale. Some of these tests can also generate pressure data, some of them can't. So we tend to use these screening tests in conjunction with each other to ensure that we've got data that aligns with each other between different tests, giving more confidence and certainty in the results, but also to complement that temperature heat flow data with pressure generation, pressure rise rates, and so on. So yeah, as I've said, regions of interest highlighted during this screening phase can be studied later on in adiabatic methods, which take longer run times, greater sample amounts, and more analysis to report. Which leads us neatly into the adiabatic calorimetry. So as I said, these tests are typified by slightly larger sample requirements than the screening test. So it's good to key into, yeah, those pilot plant scale stages where there's generally more material available to a client to provide for testing. Because they use larger sample amounts, they are also easier to representative heterogeneous samples and mixtures, which is of a lot of importance when we're talking about reactive chemical systems, where we may have a heterogeneous reaction mixture. Maybe there's a catalyst in very small amount as a solid, and it's really hard to make sure that you've got a very representative sample of that mixture if we're doing a DSE test, for example, which has a very, very small sample requirement. These adiabatic tests all have pressure data available, which again is where this information is much better for ensuring that your plant or reactor system is adequately designed to cope with any pressure generation. They of course have greater accuracy and confidence in the results. They tend to be a lower phi factor than the screening tests, so they're either easier scaled to bulk systems or they're directly scalable to bulk systems. And they also have a greater sensitivity for temperature increases or heat flows. But this is a trade-off against the tests typically taking longer, up to a day, up to 3 days to perform each test in these kind of equipment. And then finally, for chemical reaction hazards testing is the reaction calorimetry aspect. And this is really looking at characterizing the actual desired process that will be performed on plant. And again, this comes in, or it complements well in a new process development journey. When we're optimizing a synthetic route, we're looking at taking to pilot plant. We want to know, both from a quality perspective, are you dosing things correctly? Are you getting any accumulation of reagents if you're dosing too quickly? The kind of agitation speed, if it's sufficient to keep heat removal under check, and yeah, also to quantify really the cooling capacity that you will need at bulk scale to keep any exothermic reaction under control and not triggering a thermal runaway scenario. So the reaction calorimetry really can be performed at a variety of scales. We can use some of the equipment in the previous slide to do reaction calorimetry as well, but the equipment on this page are more dedicated reaction calorimeters, which tend to be on the scale of sort of 100 mil up to a litre or so. And yeah, these tests and methods need to be designed bespoke to really closely match whatever the desired process or reaction that the client is wanting to perform as closely as possible to really simulate their desired process. So these are all really accurate systems, and they, yeah, as I've said before, they help us with a variety of parameters that we require for plant equipment design, and also informing on processes and operation of those plants. So this kind of all feeds into how we choose various tests, and as I've highlighted, these tests tend to be quite complementary to each other. So to assess an example reaction with 3 stages, we'd propose initially, if there's a lack of information to begin with around the thermal stability of mixtures, premixes, products, and so on, we would first look to do thermal stability screening of those mixtures and products to sort of highlight or study whether there is any thermal stability decomposition type potential, but also to perform the reaction calorimetry and really test the desired process and reaction that the client wants to perform. And this kind of information, pending the results from this, we may propose further adiabatic testing or vent sizing type testing, depending on the results and if there's any potential for thermal runaway to occur plausibly. And this kind of ties back into this chart from the Francis Stozel book that I showed before. If we do the reaction calorimetry and it shows that the reaction is never going to generate any particular amount of vapor pressure, or it's never going to reach any decomposition in the materials present, then it really is a low risk system, and the potential requirement for further testing is low in that case. So we'll move on now, leaving the reactive systems, chemical reaction hazards testing to the industrial explosion hazards focus testing, and just to look at the conditions for dust or powder explosion to occur. So the material must be flammable. These are the conditions and criteria for the explosion pentagon that we can see on the right hand side. So yeah, the material must be flammable or combustible and dispersed or airborne to form a cloud. Secondly, the concentration must be within explosible limits. So I referenced that slightly earlier with the gas and vapors testing, where we have a lower and an upper explosible concentration, where the mixture can either be too lean or too rich to support combustion. Thirdly, the particle size distribution should be capable of propagating a flame. So that's the difference in this case between a flammable material, solid as a bulk, and a dust cloud. That categorization of a dust varies slightly between whether it's European regulation or American regulation, but sort of less than half of a millimeter is the size of a dust to categorize as a combustible dust in this case. Fourthly, the atmosphere in which the dust cloud is dispersed needs to support combustion, so it needs to have oxygen present and a sufficient level of oxygen to support that combustion also. And then finally, we have to have the presence of a sufficiently energetic ignition source to actually kickstart the combustion. So there's a variety of tests that can really look at each individual criteria really for the explosion pentagon. Firstly, to categorize a material as combustible or not, as a dust or powder. And then secondly, to look at the sensitivity of the material. So sensitivity to the ignition source, whether that's energy, electrostatic, or temperature. And then also sensitivity to do with the concentration requirements of the dust cloud that I mentioned earlier. And then finally also the oxygen. So what is the lowest amount of oxygen within the system to actually support the combustion of the dust cloud. So this is appropriate for systems that might have inerting present with nitrogen or argon headspaces, for example. And then finally, explosion severity. So this is kind of exploring the worst case scenario of this explosion pentagon, where we've got all 5 criteria in their optimum point, and what is the maximum explosion severity of the material under those conditions. And then finally, we have sort of burning behavior, burning rate, and these are more to do with transportation and storage of materials rather than being dispersed as a dust as such, as a dust cloud. So for this testing and these assessments, and again, to ensure that the data is really relevant to your process and your scenario, the material parameters of the dust are really key. So the chemical composition of the material, it's probably taken as a given that it will be in the same form as when it's tested. We don't expect the composition of the material to really be different. But there may be some cases, certain materials sensitive to oxidation, that we need to ensure that they're transported appropriately from a client site and then tested properly also to ensure that they haven't gone through some kind of chemical reaction to change during the shipping process. Secondly, which is really critical, is the particle size of the dust or the powder. And again, to get the data relative to your process, this particle size really should be representative of kind of a worst case that could occur in your process. So we would guide on some caution on using any kind of data from MSDSs that's already provided. If you buy a material from your supplier and they state a MIE value, MIT value, explosion severity, there's no guarantee or certainty in what form the material has been tested to get those values. So if you receive a material that is 500 micrometers diameter, and then you're purposely milling it down to reduce the particle size, we don't know whether the data on the MSDS is going to be appropriate, or it may be way off the mark for the actual material you're handling with that smaller particle size. Again, Also, is the sample chemically pure, or is it going to be a mixture or a blend? That'll really dictate on the most appropriate way to prepare the material for the testing as well. There's quite a few niche things to consider on that one. Moisture content as well. The moisture content of a sample really will have a big effect on the results, on the outcome of a test. So especially for milling operations, any processes that have hot motors, we can imagine that when a dust settles on these surfaces, there's a very reasonable potential for these materials to dry out over time. So it's really important to think about the moisture content of the material, and should the material be relatively dry in effect before testing to give a reasonable worst case result. Kind of linking into particle size at the end, we have particle morphology and surface area. This can impact on the results, but have less of a bearing on the results than particle size does. And again, to ensure it's all relevant to your process, we need to focus on what is a reasonable worst case. So just some excerpts from literature just to try and demonstrate this particle size dependency on results. For the top two plots, we have minimum ignition energy on the left-hand side and the particle size diameter on the x-axis. And we can see in both cases, I think the right-hand graph is an aluminium particle, and then the left-hand is polyethylene. We can see quite a sharp downward trend in effect, where the particles go from hundreds of micrometers to tens of micrometers. The ignition sensitivity of the material gets much, much lower. The same is true with explosion severity with this bottom graph. So these are different types of milled wood powders. And we can see that as the particle size decreases from right to left, the explosion severity parameter, the KST in this case, increases and increases more quickly at the lower particle sizes. So as I said before, this kind of range of combustibility, dust and powder tests tend to look at specific criteria of the explosion pentagon, whether it's looking at sensitivity of the material to ignition or the severity of it. And again, we should really choose which tests and which data we want to go for, tailored to what kind of operations are going on plant and what kind of operations the material will be going through. So if we take sort of silos at the top, that is obviously storage of a material, in which case thermal stability testing may be advised to ensure that on a hot day we don't have a runaway reaction of the material decomposing, but also minimum ignition energy, so assessing any risk of electrostatic sparks to ignite the material either during loading or unloading of the silo. And then we can see further down, size reduction, milling operations, ovens and dryers. Again, thermal stability, any kind of elevated temperature concerns and decompositions. Minimum ignition energy, we can see this is all the way through the operations because there's a potential there for any movement operation of a material to generate electrostatic sparks as an ignition source. But then also on ovens and dryers, size reduction, minimum ignition temperatures of clouds and layers become important in this case. And then moving also to thinking about gases and vapors, we can consider the same kind of explosion pentagon, but rather than combustible dusts or a dispersion of dust particles, we can just replace that with a gaseous atmosphere, flammable gas, flammable vapor, and the dispersion of that vapor and gas. So we can move from the kind of simple tests with flashpoint of different setups with closed cup or open cup, and that is very simple to see if we can ignite the vapor headspace of a material through a temperature range. And then if we find that a gas or vapor is indeed flammable, we can look at the sensitivity of that to various ignition sources. Again, electrostatics, elevated temperature, and these explosible limits, lean and rich mixtures. We can also test for explosion severity in this case. Again, the optimum of this explosion pentagon. What is the maximum explosion parameters we're going to get from this material? So just in the same way as the dust tests before, these individual tests are kind of keyed to looking at different parameters of the explosion pentagon. This is kind of a handy graph again from literature that details the various gas and vapor flammability points and the regions that the tests we use highlight. So flashpoint tending to be the lowest flammable atmosphere temperature. We've got the upper flammability limit and lower flammability limit with the lean and rich mixtures, but also the auto ignition region where the only ignition source is elevated temperature. So there are some, again, calculations that can be done early stage to approximate what flammable limits may be. And this, if we have a material that has a very wide flammable limit, it may be decided that it's not worth progressing with using that material further down the line. But again, these are just used to inform and estimate flammable limits and stoichiometric compositions for flammability. And then finally, the last core of testing, which again should feed into the full assessment of any process or operations on site. So electrostatic assessments of material or moving material, so charge relaxation time, resistivity of materials, chargeability through moving the material, and on the bottom row we have thermal stability testing, specifically geared towards inert materials for transportation and storage in silos and so on, but also for design of dryers and spray dryers. So to tie in all of this testing data that can be gleaned from all of those tests we've run through, again, are the variety of different process assessments available and the regulations that enforce those. So hazardous area classification and DESIR kind of looks at, is there a potential for flammable atmospheres to occur? The DESIR can also cover reactive systems. So if there's a potential for a vapor pressure or gas pressure to accumulate, it doesn't have to be a flammable vapor, but if it's within a contained system, there is potential there for an explosive atmosphere due to the increased pressure. The HAC classification and dispersion modeling can predict areas and regions where flammable zones may exist. And then going more detailed after that, process safety management are processes in place sufficiently low and high level to ensure that processes and explosive atmospheres are managed properly. HAZOP is very specific about highlighting and can really help identify worst case scenarios for a new process and inform on testing that's needed. LOPA, looking at existing controls and what else, whether they're sufficient to de-risk the process, and functional safety can really tie in all of these different kind of assessments and ensure that they're complementary. So as a quick summary, I hope we've emphasized that testing to be used should be selective and appropriate to the design of your process, the materials used, and the operations. Assessment should really consider all reasonable eventualities. We don't need to go over the top, but anything that can reasonably occur should be considered strongly. Any changes to a process, material, or equipment should be considered fully. And we've also looked at what these potential causes are of runaway events and potential scale-up issues. So that brings us to the end of our talk today. Thank you so much for everyone attending. I hope it's been useful for you. Of course, you can reach out to us on any of the details on this last slide or through the website. If you have any questions or inquiries you'd like to put to us, we can really help you scope on what kind of testing may be appropriate for your assessments. So once again, thank you very much, and I'll see you again.